Hey, welcome guys. Yeah, so today I want to talk about the structure of groups. Yeah, so basically in the previous video we already talked about pseudo theorem. So the next few video about group theory, I plan to cover the direct product and go to the abelian group, the classification of abelian groups. And I already talked about symmetric groups, so I want to talk about the solvable groups. And also the general linear group. I think this is yeah, so this is after the pseudo theorem. So okay, maybe I will give another video about alternating group. I think this is pretty much the group theory that I will cover. So maybe 5 or up to 10 video, and I will close the group theory video and I move to the Galois. Okay. So today I want to talk about direct product, and I also want to talk about some number theory application like Euler phi function. Okay, so let's start. Okay, so let's give a let me just give a definition. So suppose I write G1 cross G2 if both are groups. As a set, they are just a Cartesian product. And yeah, some people use this notation. So yeah, I like to call it direct product, or maybe sometimes direct sum. But actually they are different, right? But in a group theory, that somehow the definition is only the definition is really clear, so that I think I think there will not be a confusion. So Cartesian products, the element, let's say called x1 and x2, y1 and y2. Then the definition of the group operation is x1, y1, and x2, y2. Okay, so so easy verification for you to verify that G1 times G2 is a group. Okay, so this is very simple. So just leave it to you. Okay, and obviously that you can talk about G1 cross G2 up to cross Gn. So yeah, basically the operation is x1, x2, xn, y1, y2, yn. The group product defined to be the each group product on point wise, okay, or component wise. Okay, so okay, so this video has only one theorem I want to prove. Okay, so theorem, which is the only important theorem in this video, is that G is isomorphic to G1 cross G2 if and only if there exists a two normal subgroup, let's say A and B of G, such that the first one, A intersection B, is identity. So A intersection B only contains identity, and the second is that A times B will be G. So this is as a set, right? So every G element can be written as A times B. And this is one kind of treatment. Okay, so another treatment will some people will define will say this theorem require the uniqueness of A and B, but actually in this content, that the uniqueness will occur when it satisfies this relation. Okay. Yeah, so this is the only thing I want to prove. Maybe let's see. Let's prove this direction. Okay, so okay, so obviously that suppose G is isomorphic to G1 cross G2, right? I can I can define a two projection. Okay, and this projection is trivial. Just send x1, y1 to x1, and x1, y1 to y1. Okay. and I can ask what is the kernel, right? So the kernel pi1 basically is x and y, and x is what, right? So let's say x belongs to G1, y belongs to G2, and the kernel pi2 is the same, right? So just x, y, and y is 1, okay? This is very stupid, right? Okay, so you get two kernel, and obviously, and we just, I know this is very elementary that we know the kernel pi1 and the kernel pi2 are normal subgroup of G, right? Since they are kernel, and obviously that this kernel just map fix x1. This is the first component to be 1, right? So kernel pi1 is isomorphic to G2, and the kernel pi2 is isomorphic to G1. Okay, so very oh, sorry, I didn't say. So suppose there is two normal subgroup A and B such that these two satisfy, and establish that A isomorphic to G1, B isomorphic to G2. Okay, so yeah, sorry, I didn't say this. Otherwise, these two theorems do not connect. Okay, but okay, so basically the kernel pi1 G2, kernel pi1 G2, kernel pi2 G1, right? So yeah, so obviously if this is true, then now we already get I can that is A G1, that B is G2, and they are normal. So I basically already verify these sentence and these sentence and these sentence. I only need to verify their intersection in 1, right? But by this definition, right, the kernel pi1 and pi2 only the only intersection is 1 and 1, right? So by definition, they are 1. Okay, so the remaining is maybe to show that AB is G. Okay. Okay, so finally, just need to create isomorphism, right? So let's theta to be G1 cross G2. Let's say go to G. Let's see. Okay, so that's yeah. So finally, I just need to show that AB equals to G, right? So basically, G1 times G2 as a set equals to G. So my work is just define a theta G1 cross G2, right? I map to G by just assuming. So let's assume this theta is isomorphism. Okay. So suppose so if now theta is isomorphism, then obviously that the G1 is just the theta of kernel pi2, okay? And the G2 is just theta of kernel pi1. Okay. And as I say that the kernel pi2 is isomorphic to A, isomorphic to G1, and the B is isomorphic to kernel pi1, and as isomorphic to G2. Obviously, their intersection is trivial. And obviously, from here, these two, you get AB is equals to G. Okay. Yeah, I mean, I didn't write anything. I didn't write anything non-trivial, right? This direction just once you define this pi1 and pi2, then obviously that you just you can just see that they both they satisfy all this relation. Okay. Okay, so the actually some a little bit non-trivial part is that how to the other direction. Okay, so now let's say I have a normal subgroup of G and a B normal subgroup of G, and then AB is G and the A intersection B is 1, right? And I want to claim that G is isomorphic to A times B. Okay. So this part is a little bit tricky. So proof. Let's see how to do a proof. Okay, so since G is AB, right? So any G can be written as AB. Okay, and let's say we first show that this is unique. Okay, so unique, suppose it's A prime B prime, then you get A prime inverse is equal to B prime B inverse, right? So this is A, this is B, but actually their intersection only identity, right? So by this construction, you know that A prime is A, B prime is B. Right, so actually the way is unique. Okay. Okay, so now I can create. Let me just create a home bijection. Right, I want to create a bijection from A times B to G, right? And the proof that this is isomorphism. So that's A times B onto G, right? By definition, you take any G, which you can write it as A B, and this is unique, right? So I just show that this sentence show that theta is 1 1 and onto. Right, so the final thing is to show. Finally, we just need to show theta is homomorphism, right? Because it's 1 1 on 2, so if theta is homomorphism, that is isomorphism. Okay. Yeah. So this map is just A times B, A and B map to AB. Okay. Okay. So hopefully this is easy for you. So if you start from AB and then A prime B prime, right? Let's say you account theta, so it's basically theta A prime, right, and B prime, right? This is the definition of the A product B, the group operations, right? So if you take these two, by my definition, I make this to this, and which tell you that this is just A prime, B prime, and by definition, right? By this, okay. So yeah. So now, right, so we need to evaluate this, right? But notice that notice that the AB actually commute. Okay, the reason is that right, we know that for all A and for all B belongs to A, for all B belongs to B. We know that let's say A B, A inverse, B inverse. Now here comes the magic part, right? So this guy is this guy. So here comes the magic part that from this up to this, I didn't use they are normal, right? I only say that I only use this and this. So I use these two conditions that I can already prove this is onto. But in order to prove this is homomorphism, I need to use AB are normal. Okay, so now here comes the important part. Since AB are normal to each other, sorry, AB are normal in G, then this guy, right? This guy is what BAB inverse, right? So this guy belongs to A. Okay, this guy belongs to A. So what I'm saying is that we know that A inverse B inverse, this guy belongs to A, right? So this guy belongs to A. So this is first result. And the second result is that A inverse B inverse can also be written as A inverse B inverse. Since B is normal, so and B, so this guy belongs to B and this belongs to B, right? But the only AB intersection is identity. Okay, so I get the A inverse B inverse is only identity. It can only be identity. So AB equals to BA. Okay, so AB commutes. So I go back to here. And then using AB commute, right? So I can written as AB A prime B prime. So obviously this is just theta A B. Right, theta A. Okay, so theta AB is AB, right? And theta A prime B prime. Okay, so theta is a homomorphism and the 1 1 and on 2. So basically we prove this theorem. Okay, so this theorem is that the people usually use this to determine whether the group can be actually written as the direct product. Okay, yeah, so this is the whole proof. Okay. Okay, so actually from here that we can immediately get one result, the theorem. Right, so if we start from finite abelian group, right, suppose our G can be written as this G can every finite can 100% written as the product of the prime power, right? Because any positive integer is a product of primes. Okay. And obviously that from the Euler theorem, I know that this G must have the P1N1 subgroup and the P2N2 subgroup, right? PK and K subgroup, and they are all intersection to be identity because they are co-prime to each other, and their product will be G, and they are all normal because they are abelian. So from the previous theorem, I know that the G is isomorphic to the product of the Euler group. So the product of the Euler group of G. Okay, this is the first results that of the finite abelian group. Right, but in general, actually, one can prove the stronger results that the finite abelian group are direct sum of the cyclic. Right, but the proof need to be polished. That not just need to use this one. So you need to more results to prove that it's actually direct sum of cyclic. But in this video, I only use this theorem and say that you can at least get it to be the product of the Euler group. Okay. Okay. So yeah. So let me just okay. So let me just cite the results. So the finite abelian group. So I will give the proof in the future. Okay. So finite abelian group is actually isomorphic to the product of cyclic or direct sum of a cyclic. Okay. Okay, so for example, if you want to find a group order 100, and this is an abelian, then this guy is let's say right. So you can get this, and then you can easily. So the only case are Z2. There is on Z2, there is on Z5. This is the first case. And also Z4, there is on Z5, and the Z4, there is on Z25, or Z2, or also what Z2, there is on Z2, there is on Z5, 25. Okay, so these four are all the cases. Yeah, I think all the four cases of the group 100. Yeah, hopefully I'm correct. Let me see whether I missed something. I think I don't miss anything. Yeah, hopefully. Yeah. So totally you will have, in this case you will have 4 of it. Yeah, 4. Okay, so let me just talk about the Euler phi function and also some results. Okay, so the theorem, which is I think it's very old, right, from ancient or some, and 2,000 years ago, is that one way to write the cyclic group Zn, direct sum with cyclic group Zn will be isomorphic to n times n if they are co-prime to each other. Okay, so this is a theorem that I want to tell you. Okay. Okay, so let's give it a proof. Okay, so the proof, let's see. Okay. So I start from Zn, and obviously that I know that this guy is generated by the element C, right? So, and the order is Mn. And so obviously that Cmn is 1, right? So Cn m is 1, and also Cmn is 1, right? So which tell you that Cn has order m, and the Cm has order n. Okay, so by using the previous theorem, I know that the Cn and the Cm is a normal subgroup of Zmn since they are abelian, right? So they must be normal, and then its order is Zm and n. Okay, and the Cn is cyclic, right? So this guy is just Cm and the Zn, and they are their intersection is identity, right? Because their greatest common divisor is 1. Okay. Yeah. Okay. So yeah. So somehow now it seems like we only need to so it already satisfy the normal conditions and the satisfied intersection is identity, right? So the only remaining need to show the only remaining is to show show what? Show their their products, the whole group. Okay. Oh, sorry. So this is A. This is B. Okay. Yeah. Okay. So notice. So now we just need to show this, right? But this is the same as I just need to show they can produce identity. Okay. But we know that there is a theorem called go back to 2000 years ago. The Euclidean algorithm says that if things m and n are coprime, right? So there exists the integer u and v such that un plus nv is 1. Okay, so which tells you that your original c, the generator c here, can be written as cum plus nv, which is cmu times cnv. Okay, so now identity here can be generated by a and b. Right, so by this, so which means that you can generate everything. Okay, so basically AB is just exactly the M as a set, right? So by the previous theorem that it satisfied all 4 conditions, so we just prove. So now coprime is very important, right? By the Euclidean theorem. So the M is isomorphic to the M direct sum Z. Okay, so now we can prove the famous result about Euler phi function. Okay, so I think everyone knows about Euler phi function. If you don't know that, maybe you should leave my video. So the phi of n for each n greater than 2, I think greater than 2, will be the number of the let's say the number of integer or positive integer is coprime to n. Okay, so for example, 5 of 10 will be number of the positive integer is coprime to 10, right? So it should be 1 and 3 and 2 cannot be, right? 2, there's 10 here, 4 cannot be, 5 cannot be, 6 cannot be, 7, 9, yeah. Right, so 5 of 10 will be 4. Okay. Okay, so this is one definition. So another definition is that this phi n should be this phi n, right? So phi n can be defined to be the order of the group, which in the cyclic group of n in the multiplication, but and only so this is Zn group in the multiplication, right? So only this Zn, the inverse the element which it has inverse is the element which is coprime to original n. So this is the elementary number theory. I think it's junior high school or something. Yeah, so yeah, this is one definition. Okay. Okay, so let me just tell you how to the usual computation. So one computation is that when p is prime, obviously when p is prime, right? So phi of p will be 1 to 2 to p minus 1, right? So just p minus 1. How about phi to a p m, right? So it's prime power, and obviously that you just need pn and the minus total is pn, right? You need to minus which is not coprime to p, right? But each p element will give you one number coprime to p, right? From 1 to p, there's a guy which do not coprime to p, which is p, right? So the density is pm divided by p, which is pm minus 1. Okay. So finally, but how about how to compute the, let's say P1 R1, P2 R2, Pn R, right? This is the goal. Okay, so there's a theorem which if GCD Mn is 1, then phi Mn is equals to phi m times phi n. This formula is commonly used and commonly shown in other video like the quantum computing or something, but seldom people know how to prove. Okay, so the proof is basically from this, right? Basically from this. Okay, so okay, so yeah, basically from this. Okay, so let me just give you the more detail. Okay. Yeah. So let's see. Let me just tell you how to write how to prove this. Okay. So from this one, right? From this one I know that the ZMN, right, is isomorphic to ZM times Z. So this tell you what? This tell you that if you write element, right, let's say this is XY, right, and the product K to be zero, to be 1. So if this is the case, then if and only if which xk is 1 and the yk is 1, right? So that means the order of the xy will be the least comma divisor, will be least comma multiplier of the order of x and y, right? From this to this. But they are co-parent, right? So the least common multiplier of mn will be mn, right? So obviously that if you take the multiplication inverse, then you will get, and then take the order, you will get this one. Okay. Right, this is just a reason. Yeah. Okay. So from here that we get this is just 5p1 r1, 5p2 r2, 5p and rn. And you can use the previous formula. So finally you will arrive the famous results that 5n is defined. Can be written as n times prime, which is divisible by n, and 1 times 1 minus p. And the proof we just write, and these guys are p1 r1 1 minus 1 minus 1 minus p1 divided by p1, right? So finally you get the p1 r1 pn rn 1 minus 1 over p1 1 minus 1 over p2 1 over 1 minus pn, and then this guy is n, and this is the product of 1 over p. Okay, yeah, so this is the final results. Okay, so this is actually the final theorem about Euler phi function. Is that if you sum over all the d, right, which D is the subset, D divides n, then you get original n. Okay, so this formula is very looks actually it's very non-trivial when I first see this. So for example, let's see if n is 6. So you get 6 should be equals to phi 1. Phi 1 is defined to be 0. Okay. Phi 2, phi 3, and phi 6. So let's check this. So phi 1 is 0. Phi 2 is 1, right? Because it's 2 minus 1, and, plus 2, and this guy is 6 times 1 over 1 minus 1 divided by 2, 1 minus 1 divided by 3, right? So this guy is 6 times, right? So it's 2. Well, shit, I missed. Sorry, yeah, sorry. Phi 1 defined to be 1 because 1 is coprime to each other. Okay, so total you have 6. Okay, so the reason, the proof. So the proof is that very easy. So let G to be C has order cyclic group. C group has order n. Yeah, so basically I just say that G is Zn, right? In the right Zn, and you can and there is a fact that I didn't. Let me just quickly prove it. So in a group G equals Zn, there has exactly has exactly phi n. There it has exactly phi n element with order n. Okay. Okay. So the reason is that let's say so G is C, right? Cyclic group with order. So basically G is this, and I use multiplication notation. So let's see. Right, so I know that suppose K is chooses to release. I know that the order of the CK, order of the CK the order of the ck will divide n. Okay. The reason is very simple, right? Suppose this is ck n is cnk, right, which is 1, right? So we know that so we start from here. We know that this ck has order n. This ck has order n if and only if k and n are coprime. From this relation, okay, right? Otherwise that if k and n are not coprime, that means the c of k can attach something which is go to n, right? So for example, if n is even number and the k is n divided by 2, then cn divided by 2 square will be n, right? So it will be order 2. So ck has order n if only if k and n are coprime. Okay, so which just prove this sentence: G equals Zn has exactly phi n element with order n. Okay, so from here that I can prove these results. Okay, the reason is that I can just take, right? So I can okay, so let's say every divisor d of n, right, is the unique Sigley group. Right? It's a unique Sigley group. Is the unique Sigley group of G. It's a unique Sigley subgroup. Okay, so remember that G is just Zn, right? So I think every subdivisor D of n is a unique Sigley group sub G. U is a unique Sigley subgroup of G. Let's say A, D, and D. Yeah, I should say it's the order. Sorry, it's the order. It's the order of a unique Sigley subgroup of G. Yeah, so this makes sense. Okay, then this is right. So what is that subgroup? That subgroup is just D, right? And x belongs to G, and the xd to be 1, right? So this D just CD. Okay. Right. So the total element. If you take the element, you get n. Right, and each element has one particular order, right? Each element has one particular order, and that order must be what? That order must be the divisor of n, right? And how many of that? So how many element with the order d? Exactly 5d element. Okay, so total you get this. That's it. Okay, so right, so yeah, that's it. So see you guys next video. Yeah, so hopefully subscribe to my channel. Thanks.